Welcome to another Talking Hand video, and this video is called Q for an RCL circuit at resonance. Okay, so let's take a look at a circuit. Okay, we have some kind of generator. Oh, we don't need a generator, we're going to have it just resonate. So we're going to take a resistor, a capacitor, and an inductor in series resonance. And we know that the resonant frequency for such a thing is equal to 1 over the square root of LC. And then if we put a 2 pi there, we get frequency in hertz instead of, if you remember, I derived it one time in a previous video where we had it in radians per second. So what is Q? Well, the formula for Q, there's a couple ways of finding it, is X of L over R. Now notice this is dimensionless, okay, because this guy's ohms and the bottom guy's ohms. But what does Q do? Well, suppose X of L is 1500 ohms. And let's say R is 100 ohms. Okay, that gives us a Q of 15. Okay, of 100, yeah. And let's look at another example where this guy's 1500 ohms. And let's let R be 10. So this ratio is 150. Well, that doesn't mean much, but if we graph these, we'll see what happens is, if you look at the frequency that these things generate in comparison with a bandwidth where it's not a particular frequency, here's just your frequency of resonance, and notice it spans a range of frequencies, and here's, let's say, voltage. Well, right there, that's the resonant frequency as determined by this formula. You can see that there's a particular bandwidth here of a range of frequencies that's used. Also, you could have it go more like this, where it's wider. Okay, where you have much wider bandwidth. Okay. So, and here's your resonant frequency right there. This is for a high Q. A high Q would be maybe 150. So notice it peaks at a very narrow frequency range. And this would be for a low Q. And this would be perhaps the 15. Okay. Now, which one of these do you think would be better for a digital signal? Well, since digital is ones and zeros, I would pick this one because it takes a very little bit smaller hunk of the electromagnetic spectrum. Okay, so a typical, the way they would design these typically, if you put your X of L about equal to 1,000 ohms when you design this. Okay, and what that allows you to do is most of, if you remember that just the inductor will have self-resistance because it's a coil piece of wire. So it has so many ohms per foot in there, and it might have many, many feet. So it contains resistance anyway, whereas the capacitor doesn't. Okay, and you could design it X of C over R because at resonance we know X of L equals X of C, right? That's the whole point. Okay, but since the capacitor does not have that resistive property like the inductor, it's usually designed via the inductor. Okay, and we're not going to get into output impedance and antenna design, but it has a lot to do with that as well. Maybe that's a separate video. Okay, so let's take it and explore bandwidth a little bit. Okay, how do we determine bandwidth? Oh, here's your resonant frequency, and let's just say that this output is 100 volts. Okay, that's all huge output, but 100 is a nice number. That's your resonant frequency. There is a point here on the left side, or the low frequency, and a point there on the right side on the higher frequency. This thing's usually called F1 and this thing's called F2. What a surprise. Where this point is 70.7% of the top. Now you'll probably recognize 0.707 is the cosine of 45 degrees. Okay, having a lot to do with power factor. So this width of frequencies between them is called the bandwidth, abbreviated BW. Okay, and if you know F sub O, we could find F sub O because we could use this formula, 1 over 2 pi square root of LC. We could find F1 and we could find F2. Okay, so it's actually pretty simple to do that. So another way of calling the bandwidth, sometimes they call it delta F, but the bandwidth is equal to the resonant frequency over Q. So you could find that. And then you could find where F1 is. So if we just find the resonant frequency and subtract this many hertz over, okay, which is half of the whole bandwidth, so we could see that F1 has to equal the resonant frequency minus the bandwidth over 2, half this width. Okay, and so F2 has to equal the resonant frequency plus bandwidth over 2. Okay, so these are things that you could find. Okay, so we're going to have a worksheet that has to do with finding out some specific things for the radio station Cameo. Okay, which is equal to 106.1 megahertz. And I'm going to have you guys find L and C for this circuit to resonate at that frequency. If you do this right, this should be in hundreds of picofarads. It's probably a very small number. Okay, and we're going to establish a Q and find F1 and F2. Okay, do the problem sheet. Look at this video a couple times if you have to.